Citric acid and citrus juice. The aim of this experiment was to determine the content of citric acid in citric juice by titration. The experiment was split up into 3 parts. The first part involved doing a colorimetric titration of a solution of citric acid. In this form of titration, the endpoint could be seen on the macroscopic level by a change in color because of the pH indicator phenolphthalein, which changes the color of the solution when pH is between 8.2 and 10. In the second part, we did a potentiometric titration by measuring pH with a pH meter. This was still titration of citric acid. This part was done to draw a titration curve of the titration of citric acid. The endpoint could be seen by a drastic change in pH and a steep curve. In the last part, we did both a colorimetric and potentiometric titration of citrus juice, which contains citric acid, and this was done to determine the concentration of citric acid in citrus juice. Experimental setup and procedure. On this slide we can see all the equipment and chemicals used. It is duly noted that sodium hydroxide is corrosive and therefore should be used with caution. And on the right we can see the setup with the pH meter. First part of the experiment. In the first part of the experiment, we did a colorimetric titration of 25 milliliters of citric acid. The solution had a concentration of approximately 0.03 molar. We titrated this solution with 0.1 molar of sodium hydroxide, and the endpoint could be seen at the macroscopic level by a change in color, which was pink, as you can see on the right. This color change was caused by the indicator called phenolphthalein, and the endpoint volume was noted to be 19.4 milliliters, which was the amount of sodium hydroxide used. Second part of the experiment. In this part we did a potentiometric titration, still of 25 milliliters of citric acid. It was the same concentration as before, which was around 0.03 molar. As before, we titrated again with 0.1 molar of sodium hydroxide. And the goal of this part was to draw a titration curve as seen below, and we noted the endpoint out from the titration curve to be 19.5 molar. And we can therefore argue that the results of part 1 and 2 are in accordance, as the endpoint volume is basically the same, whereas the volume from before was 19.4 milliliters, and this one is 19.5 milliliters. And the endpoint could be seen by the drastic change in pH from a single drop, and it was the steepest part of the curve. Last part of the experiment was where we squeezed citrus juice out of a lime, and we then diluted the 20 milliliters of citric juice into a 250 milliliter solution. And then we transferred 25 milliliters of the diluted solution to a beaker and carried out our titrations. And we did both a colorimetric and potentiometric titration. We then drew a titration curve, as you can see here, and the endpoint was noted to be 17.5 milliliters of sodium hydroxide. To further understand the chemistry going on, we have to look at the reaction schemes. However, we could also talk about pK values first. The higher the pK value of an acid, the weaker it is, since it dissociates less. Acids can therefore be classified into different strength classes, whereas a pK value of 0 is a strong acid, and this acid dissociates completely. Therefore, the reaction schemes of these acids are written as an arrow. A pK value of 1 and between 1 and 4 are called mediocre acids, and at last a pK value of 4 and over are weak acids. Both mediocre and weak acids are reversible reactions as they don't dissociate completely. As seen in the reaction schemes to the right, the reaction can be split up into 3 different reactions. The first one describes how citric acid reacts with hydroxide ions to lose a hydrogen and form water. It then becomes a weaker acid with a higher pK value and reacts with another hydroxide ion to form an even weaker acid and water. This weaker acid reacts with another hydroxide ion to form a weak base. And this can be used to explain why there's only one endpoint that is visible. The first 2 endpoints is when each acid is used up completely, but there's no drastic change in pH since becomes another acid. But the last product is a weak base which causes the pH to increase drastically, as seen on this steep curve, and it's the third endpoint. and we found the endpoints of each one by dividing the third and last endpoint with a third, since it was 3 reactions. And then we found it to be the first one to be 6.5 milliliters, the second to be 13 milliliters, which is 2/3 of the last endpoint. pK values of citric acid titration curve. So we had to find the pK values of our titration curve, and we did this by dividing each endpoint with 2. And we then compared it to the textbook data. And as you can see, there's a slight difference in pK values, and this is because that we had to calculate them out from an endpoint, and the endpoint might be imprecise. And we also had to round up each time after dividing, which makes the numbers a bit changed. But anyways, the pK value as seen here is only slightly different and isn't that far off, which is a good thing. Concentration of citric acid in experiment 2. So we had to find a concentration of citric acid in a solution of citric acid. This was done by using the concentration formula seen here. We knew that, so the amount of hydroxide ions is equal to the concentration of volume times volume, which is, we knew that the concentration was equal to 0.1 molar, which was noted back on the bottle. And the volume used was the endpoint volume, which we noted to be 19.5 milliliters. This gave us the result 1.95 millimole. We then knew that the amount of citric acid in the solution was a third of the amount of hydroxide ions, since the reactions were split into 3. So we divided by 3. So we had to divide 1.95 millimoles with 3, which gave us 0.65 millimoles. Then the concentration of citric acid was found by isolating the concentration formula, and it is equal to the amount divided by volume. This gave us 0.026 molar. Finally, the concentration of citric acid in citrus juice. This was found by using the endpoint from our graph, which was 17.5 milliliters. We then calculated the amount of hydroxide ions the same way by using the concentration formula. This gave us the answer 1.75 millimoles. The amount of citric acid was also found by dividing with 3, which gave us 0.58 millimoles. And the concentration was found by using the concentration formula and gave us the answer 0.00232 molar. And we divided by 250 milliliters because it was diluted into a very large solution. Conclusion. We found the concentration of citric acid in the solution to be 0.026 molar, and it was found to be 0.00232 molar in part 3. And we found a concentration by doing titrations and using titration curves. By looking at the titration curves, we are now sure that there is indeed citric acid in citrus juice, which is all I had to say. Have a good day. See you tomorrow.